Modern data pipelines operate under punishing execution budgets. Every millisecond, these systems are ingesting millions of requests, sorting payloads, and trying to push them through highly constrained server architectures. To prevent the entire network from bottlenecking, servers have to pack this incoming data into fixed bandwidth slots as efficiently as possible. For decades, schedulers have managed this packing process using a classic algorithmic framework known as the 0-1 knapsack. Look at this linear data pipeline. The defining rule of the 0-1 knapsack is binary. A specific data bundle is either included or it isn't, and it can be processed strictly one time. Because you can't reuse a block that fits perfectly, you end up with jagged, empty gaps inside the pipeline. Those gaps represent unused pockets of bandwidth. By treating data streams as single-use items, the system creates artificial choke points, leaving stranded units of capacity that throttle the throughput of global systems. In reality, a high-concurrency data center isn't processing a finite set of unique items. It receives endless, repetitive streams of identical data packets. If a specific 5-megabyte payload is the most efficient block to fill a remaining slot, the system needs the ability to pull that exact same block again and again until the space is maximized. Adapting to this reality requires a shift to the unbounded knapsack problem, a paradigm where the supply of any given item is treated as infinite. Removing the single-use constraint mathematically targets the highest possible density of data. The pipeline can finally transition from a static choke point into a system capable of continuous, high-volume flow. To see exactly how this unbounded logic works at the code level, we can map the algorithm's memory onto this one-dimensional array. It tracks available capacity, starting at 0 and moving up to the maximum limit. In the old 0-1 knapsack, the capacity loop calculates values by iterating strictly backward, starting from the maximum capacity and stepping down to 0. This backward motion is an intentional blind spot. It ensures the algorithm only reads old values from a previous pass. It places a block, but immediately moves past it, making it impossible to double count that item. The micromechanical fix for the unbounded knapsack is simply reversing the inner loop's code, changing a decrement to an increment, so the capacity check runs forward. Watch the forward pass evaluate the array. It finds that a specific data bundle fits perfectly at capacity index 3 and places it there. The loop continues its sweep. Milliseconds later, it evaluates capacity index 6, which is exactly double the size of the slot it just filled. Because the scanner is now moving forward, it looks back at index 3 and can actually see the bundle it just placed during this current pass. By reading its own immediate past, the algorithm creates a feedback loop. It stacks identical bundles until it reaches the highest possible density for any given container. When you zoom out from that single array, this logic cascades across massive server architectures, processing vast data streams. The algorithm operates in pseudo-polynomial time. Because its execution speed scales proportionally with the number of items and the capacity limit, the system can calculate these optimized fits dynamically. Systems engineers use this exact architecture to drive hardware-accelerated decoupling, allowing ingestion queues to operate independently of the processing pipelines. It is the same logic used by high-frequency trading platforms to manage financial token limits within massive branch and bound executions. Replacing ad hoc server configurations with mathematical optimization stabilizes processing rates and minimizes the unpredictable latency spikes found in manual setups. When a network begins choking on data, the standard reaction is brute force, spend heavily on new hardware overhauls, and expand the physical footprint. But clearing out a severe pipeline bottleneck rarely requires adding more physical servers. The shift happens at the microscopic level, flipping a single line of C++ code to change a backward loop into a forward loop. Scaling a global system comes down to how a single loop views its own history. When that logic shifts, the overhead disappears.